MAXVY.
Welcome to part 1 of MAXVY's Verilog tutorial series. In this video, we will introduce you to the Verilog hardware description language. In this section, we will discuss traditional methods used in chip design. These methods rely heavily on manual processes and physical components. Simple circuits were typically verified using breadboards. Breadboards are solderless devices that allows engineers to quickly prototype and test circuit designs. Here you can see a typical breadboard setup with various components. Breadboard allow for easy placement and rearrangement of components to test different configurations. Engineers manually place then connected components such as resistors, capacitors, and transistors on breadboards. These processes require careful planning and precise execution to ensure proper circuit functionality. This image shows a traditional testing setup with an oscilloscope and a breadboard. This oscilloscope is used to visualize the signal output from the circuit, allowing engineers to verify the performance and troubleshoot any issues. Now let's talk about the limitations of traditional chip design methods. While they have their benefits, they also come with several significant drawbacks. These methods are suitable for small-scale designs, but when it comes to large-scale integrated circuits, they fall short. It's just not practical to manually handle complex circuits with a large number of components. As the number of transistors in a circuit increases, manual verification becomes extremely time-consuming and prone to errors. It's easy to make mistakes when you are dealing with thousands or millions of transistors. This brings us to Moore's law. As you can see in this image, the number of transistors on integrated circuits has been doubling up approximately every 2 years. In the 1950s, we had single transistors. By the end of 2000, we are dealing with 592 millions of transistors on a single chip. Here is a visual representation of the evolution of integrated circuits. We started with small-scale integration and moved through medium-scale integration, large-scale integration, and now we are at very large-scale integration. Each step up represents a significant increase in the number of transistors. Finally, debugging and testing the complex circuits requires a significant amount of effort and resources. It's not just about placing the components on the breadboard anymore. It's about ensuring every single connection is correct and functions are as intended. This process is both labor intensive and resource intensive. Next, let's explore the emergence of computer-aided design or CAD tools and how they revolutionized the chip design process. CAD tools are emerged to automate and simplify the design process. These tools made it much easier for engineers to handle complex designs without that tedious manual work. With CAD tools, designers could create and verify complex circuits using software. This significantly reduced the design cycle, making the process faster and more efficient. Here you can see a variety of VLSI CAD tools categorized by their functions. They are tools for front-end processes like design entry and simulation, back-end processes like floor planning and extraction, design, capture, and synthesis. These tools offer capabilities such as semantic capture, simulation, and layout design. They greatly improve the accuracy and the efficiency of the design process, allowing engineers to focus on innovation rather than manual tasks. As circuits became more complex, the traditional methods of design and simulation were no longer sufficient. There was a clear need for more sophisticated methods to describe and simulate these designs. With the increasing complexity of circuits, engineers needed a way to handle and describe intricate designs accurately and efficiently. Manual methods were just too slow and error-prone. This image illustrates the requirements for modern circuit design, including architecture, hardware-software integration, behavior, functional verification, and more. As we move up this ladder of requirements, different hardware description languages like HDL are used to meet these needs. To address this complexity, hardware description language like Verilog were developed. The most commonly used languages are VHDL, Verilog, and System Verilog. Introduction to Verilog HDL. Verilog HDL is a hardware description language that's widely used in the US industry. It allows designers to describe hardware functionality at various levels of abstraction, making it very versatile. Verilog is used for designing and simulating digital systems such as integrated circuits or ICs and field programmable gate arrays or FPGAs. One of the main advantages of Verilog is that it facilitates the modeling, simulation, and verification of digital circuits before they are physically implemented. Let's look at an example to understand how Verilog works. Here we have a simple module. The module name is AND gate and it takes three ports A, B, and Y. This is the module name AND gate, and next we have the port list which includes A, B, and Y. And we declare A, B as inputs and Y as the output. Then we have the behavioral description of the module. Here assign Y equal to A and B describes the AND operation between inputs A and B. Finally, we close the module using the keyword in module. We will see the primary steps in hardware design process using hardware description language. The process begins with functional design, where we define the desired behavior and functionality of the system. This stage involves creating a high-level representation of the system using Verilog. Next, we move to synthesis. Here, the high-level design is converted into a gate-level representation. This involves mapping the design onto a hardware primitive, ensuring that it meets the required performance specifications. After synthesis, we proceed to place and route. This step involves physically placing the gates onto a chip and routing the connections between them. It is crucial for optimizing the design for area, power, and performance. Following place and route, we integrate the design into a complete system. System integration involves combining the different components and verifying that they work together as they intended. The final stage is fabrication. In this step, the verified design is sent for manufacturing to produce the physical chip. This is the overall design flow used to produce a chip. Advantages of Verilog. Verilog allows designers to focus on system functionality rather than low-level details. It facilitates quick design iterations and through verification processes. It has industry standard with extensive tool support and resources. Supports modular design practices enabling code reuse and easier maintenance. Compatible with other hardware description languages and tools. Have any questions or doubts? Feel free to write your comments and doubts in the comment section. Thank you. See you in the next video.